Hello and welcome. An understanding of geometry begins with an understanding of the basic geometric building blocks of geometry. These are things like points, lines, planes, and angles. Together these things form the foundation of all the geometric objects that we see prolifically throughout our culture, not only in our science and engineering, but also in our architecture as well as even our art. You can see some examples of this. Buildings both common and unusual, showing geometric angles both common and unusual. You can even see in the lower left-hand corner there I've shown some, I believe that's a form of art called cubism that involves a very angular depiction of reality. We have a lot to cover in this introductory video into geometry, but first let's take a moment for ourselves to isolate ourselves from the outside world, to spend some time intensively with each other so that we can learn this well. Not only cutting ourselves out from outward distractions, but also cutting us off from inward distractions. Empty your thoughts so that we can spend some time together, rise above thought, and embrace awareness. Take some time for that. Welcome back. Let's first begin with the most simple element, the point. And by introducing the point, I'm going to give you a question that might produce a kind of Zen-like quandary to you. And my question is, how big is the Earth's North Pole? Now, I'm not talking about the magnetic North Pole. I'm talking about the Earth's rotational North Pole. Well, that might be a little bit difficult to quantify. If I put because the North Pole is defined as the center of the Earth that is not rotating, well, that is not moving at all in its rotation. And as you can see, if I'm standing, for example, on the North Pole, there's a little bit of air involved. Is my right foot on the North Pole, or is my left foot on the North Pole? If it turns out my right foot is on the North Pole, does that mean that my right big toe is on the North Pole, or my right pinky toe is on the North Pole, or my heel is on the... You can get smaller and smaller and smaller and smaller and more accurate. You can always get more and more accurate, which is really the point of this portion here, which is to say that actual points have zero size to them. When you're trying to define a location, you can always get more and more accurate. And so it's possible to describe something that really... And so as we're attempting to describe this thing called a point, we eventually come to realize that this is something that has zero dimension to it. It has no width, no length, no height to it whatsoever. It has zero size in all three dimensions. We can see some examples of points in our popular culture. As I mentioned before, architecture is an example here. I'm showing you the top of a church steeple. I'm showing you some points that might be found on your computer or your phone, showing you locations of various places. You can see the popular Google symbol for a point, showing it's almost like a little pin that gets placed in a in a location there. You can see how this tends to point to certain locations here. I'm giving an example of a location below, and directly above me I'm showing you a server holding a plate of food, and no doubt having to make use of the highly important skill of finding the center of gravity, the center of mass within that plate, lest she drop something. So the question I would ask is, as she's placing her hand underneath this center of gravity, could she get more and more accurate with where that center of gravity is? Perhaps balance it on a single finger, perhaps balance it on the point of a pin? The answer is yes, she could do that theoretically, eventually, and get as small and smaller and smaller and smaller as possible. The center of gravity is another example of a point, something that ultimately has zero dimension. In addition to points having zero dimension, we're about to notice something that's also true about lines. The question that I have here, showing the globe in the upper left, is how big is the equator? The equator is kind of the sort of the belt of the Earth, so to speak. When it comes to rotation, it is the portion of the Earth that is farthest away from the North and South Pole. How would we define such a place? Well, if I'm trying to stand on one part of the equator here, perhaps this shoulder is closer to the North Pole, this shoulder is closer to the South Pole, I can always get more and more accurate as to where exactly that line is that I'm standing on for the equator. So I can always get more and more accurate. The point here is that lines have zero thickness to them. They have length, yes, but they do not have width or height. So these are good examples of one-dimensional objects, whereas points are zero-dimensional objects. We can also see this in the example here. I'm going to remove my face for a second and show you the Earth's orbit around the Sun here, and we're describing the Earth's orbit with a sort of an ellipse. It's actually not a perfect circle. The Earth's orbit is actually an ellipse around the Sun, has a little bit of eccentricity to it, but we might ask, what's the thickness of that line? Well, that's a line that is not truly real. We don't see that line actually in physicality. We can describe what it is, and that it's a way of tracking the center of the Earth as the Earth moves around the Sun, but there's no need to define any thickness of that line whatsoever, hence it doesn't have any thickness. Here's another example of lines not having any thickness. One other thing about lines. When we define a line, we define it as being straight, and we define it as being extended infinitely in both directions. If there's a line sitting out in front of us between me and you right here, I want you to imagine that it extends out to infinity in that direction and extends out to infinity in that direction as well. Next, the plane. We've dealt with zero-dimensional objects, we've dealt with one-dimensional objects, now we're going to deal with things that are two-dimensional. And we'll see this here as we are showing once again actually the Sun, with the Earth going around the Sun in this little, that small little circle there. And there's also a larger circle which shows how the Sun is actually going around the center of our galaxy. We can ask this question with that small circle or the larger circle. Ask the same question. The question is, how thick is that circle? Well, as you can see in both cases here, these circles aren't really real, and the surface that they define is not really real either. We sort of define it according to tracking the center of the Sun as it would go around the center of our galaxy, or tracking the center of the Earth as it would go around the Sun. So that defines a kind of shape that doesn't really have any thickness to it whatsoever. It's got length and it's got width, but it does not have any thickness to it. So it's almost like a piece of paper that is absolutely zero in thickness. This is something that's called a plane. It's a purely two-dimensional object in that it has no thickness, although it has length and width. Two-dimensional object only. And just like lines, these are things that extend out to infinity in the length direction and in the width direction, but of course not in the thickness direction. So let's talk about how we label these things. First with points. Well, I'm showing you an example of a point drawn out there, usually with a capital letter, and we describe that point as referencing that capital letter. So we say point A. Stringing 2 points together, we can connect those with a line, and so we oftentimes can name lines according to 2 points which that line goes through. We say line AB or line BA. We can say either way, it's the same line, isn't it? And the way that we label it is, as you can see, 2 of those capital letters describing those 2 points with a funny sort of line with arrows going in both directions, showing the infinite extent of that line going in one direction and the other direction out to infinity. And we can also describe this sometimes with a lowercase letter. Sometimes we'll attach a lowercase letter next to a line to describe it. We can also define what's called a line segment. This is just like a line, except it doesn't go out to infinity in both directions. As we describe it, we can say line segment AB. That is a segment of a line that stops at one point and ends at the other one. We could also say this is line segment BA. It's the exact same thing, isn't it? So it has 2 endpoints, A and B, and we symbolize it with 2 letters above which we place a line which does not have those 2 arrows going in opposite directions for perhaps obvious reasons. Lastly, we have something called a ray. An array is something that is sort of in between a line segment and a line, in that it starts at one point and then goes through the other point. So in this case, it starts at A and it goes through B. For this, we have to say ray AB. If we say ray BA, that's something different. That's where the ray actually starts at B and goes through A. That's a different thing than what we see here. It starts at A and goes through B. Hence, what we say is ray AB. And we place that line above it, showing that it starts at one point, no arrow, I should say, and extends past the other letter with an arrow saying that it extends out to infinity from there. So, and one other thing, the point that it doesn't start on but goes through is something that we call an interior point. So let me ask you, according to this chart right here, I'm going to hide my face for a second here, are these annotations here describing the same geometric object? Let's first of all take a look at these lines across the first row here. Line AB, line AC, line CE, line BD, and line BC. Well, hopefully you can see there that actually describes the same entity, the same line that's going through A, B, C, D, and E and extending to infinity in both directions. Are these the same? Now we're switching from a line to a line segment. We have segment AB, AC, CE, BD, and BC. Obviously, those things are not the same. Line AB starts at A and ends at B. Line segment AC starts at A and ends at C. Lastly, we're comparing a set of rays here. We have ray AB and ray AC. Now, those are actually the same. Ray AB and ray AC, both of those rays start at A and go through. Well, it's the same one that goes through B as the one that goes through C. So those two are the same, but ray CE is different from both of them. That's a ray that starts at C, goes through E, still extends out to infinity, but it has a different endpoint than the other two there. So take some time to take a look at this drawing up here. And you can assume that there are 2 lines there that are in fact parallel. They are running parallel to one another. They never intersect. And make use of some of those questions there and answer those in terms of the figure. Take some time to do that. Welcome back. Well, your answers might be slightly different from mine, but hopefully we can come to some agreement here. Name a ray with an endpoint of Q and which passes through P. Well, the answer I gave was QP. QM would have also been another possible correct answer. It's the same ray that starts at Q and goes through, well, either M or P, same thing. Do LM and MN, those two things being lines, represent the same line? The answer is yes. Do PQ and QP represent the same line segment? Also, yes. And lastly, name two lines that are parallel. Well, one is going to be described as RS, and the other one I've described as MP. You could also say PM, PQ, QP, MQ, or QM. There's a lot of different ways to name that second line. So if you got something slightly different than mine, take heart, that's still a right answer if it's one of the ones that I mentioned here. Well, let's talk about two lines that intersect with one another. If we have two lines, now remember these are lines, which means they have zero thickness to them whatsoever. If they have zero thickness, then when they intersect with each other, that means that that intersection is going to have zero size to it. So two lines intersect at one point. So we can see an example of that directly above me here. We have two lines that are intersecting at a point labeled A. And then number two, we have two lines that can actually coincide with each other. The lines AB and AC actually coincide with each other. That's another way in which lines can interact with each other. It's possible for them to intersect, and it's also possible for them to actually be the same line, in which case they have an infinite number of intersection points. So one intersection point, an infinite number of intersection points. Here's the third option. The third option is that they're parallel, in which case they don't intersect at all. These two lines never touch each other whatsoever. And we actually have a symbol for that, and you can see that shown. AC is parallel to BD. You can see two vertical lines placed next to each other is our symbol for two lines being parallel. If we take two rays and we connect them together so that they have the same endpoint, then we have an angle. So we've got an angle with formed by two rays that have the same endpoint. That endpoint takes on a new name called a vertex. It's the vertex of the angle, and each of those rays now form what we call sides or legs of that angle. So we can actually describe this angle in three different ways here, and I'm showing them. I'll turn off myself here for a moment here so that you can see these three naming conventions that exist for angles. The first is very simple. Just we say angle A, and you can see the symbol there for angle that we use. It's this little actually it's kind of an angle itself, isn't it? So angle A is our first way in which we could describe that angle to the left there. We can also label them with numbers. You can see a number that exists next to a curve on the inside there, so we might call this angle 1. The third is a bit more common, and that is we use a three-letter description of what an angle is. Notice if I trace out, and I'm going to bring myself back here, if I trace out the letters B, A, C, as they're listed in the name, BAC, you can see that I'm actually tracing out that angle from start to finish, through one leg of the angle, through the vertex, and then into the other leg of the angle. That's the third way in which we can name angles. So with that in mind, how would we name this angle with one capital letter? How would we name it with three capital letters? And how would we name it with a number? Take some time to do that. Welcome back. Well, hopefully this was pretty straightforward here. We can name this angle with a single capital letter. That's the letter at the vertex B, so it's angle B. We can also name it with 3 capital letters, A, B, C. You could also name it angle CBA. That's also acceptable. And lastly, we could name it with angle 1, the number 1. Angles are measured in degrees. You may already know that. You can describe a 90-degree angle as being the right angle that you find at the end of a piece of paper. You can also describe 180 degrees. Perhaps you've seen that when you see figure dancers, figure skaters that are turning around. Sometimes those turns are described as 180s, 360s, 720s, and so on and so forth, describing the number of times that they turn around. But we do measure angles in degrees. Lines DF and EB intersect at a 90-degree angle. That's a way of saying that these 2 lines are perpendicular. Angle BAC is less than 90 degrees, so we call that kind of an angle an acute angle. Any angle that is less than 90 degrees we refer to as an acute angle. Any angle that's larger than 90 degrees we call it an obtuse angle. And lastly, we have an angle BAE. If you'll notice BAE on that line there, that actually forms a complete line there. We consider that to be an angle. It's actually called a straight angle because it's actually, as you're going to see, it's a full 180 degrees. So we have 4 different kinds of angles that we've defined here. There's right angles, acute angles, obtuse angles, and straight angles. We also have some other terminology for angles. If we have 2 angles that together make up a right angle here, for example, take a look at angles BAC and DAC. See if you can find those 2 angles there, BAC and DAC. Hopefully you can see that those 2 angles placed next to each other and fitted together form a right angle, form a 90-degree angle. There's a term that we have for those 2 angles that do this. We call them complementary angles. They don't have to be next to each other, but if those 2 angles add up to 90 degrees, then we call them complementary angles. And there's another thing that we say, actually. We say that one angle is the complement of the other. Similarly, if we take a look at angles BAC and EAC, find that other angle there, EAC along with BAC, we say that those 2 angles add up to 180 degrees, so those things are called supplementary angles. And similarly, we might refer to one of those angles as being the supplement of the other angle. Again, they don't have to be sitting next to each other. They can be in different parts of any geometric figure, but if it turns out that their measures add up to 180 degrees, we describe them as being supplementary. So take a look at the angles that I've got sitting up here, and just using the 4 terminologies that we described initially in 2 slides ago, right angles, obtuse angles, acute angles, and straight angles, discern what each one of those angles are, 1 through 9, to describe which kind of angle each one of those angles is. Take some time for that. Welcome back. Well, you can see there that it's pretty easy to see oftentimes which category your angles fall into. Angles 1 and 3 in the first figure are obviously acute angles. They're less than 90 degrees. Similarly, angles 2 and 4 are greater than 90 degrees, so they are obtuse. Angles 5, 6, 7, and 8 are all right angles. You can see that from those two parallel lines, AB and CD, coming together in 4 right angles. And lastly, the angle that's shown there by angle 9 is a straight angle, 180 degrees. Now let's talk about what it means to describe two angles that have the same size here. We actually use an unusual word for saying that two geometric forms have the same size. The word that we use is congruent, and the best way of describing it is to say that if we take one of these, in this case, angles, we pull it off the page and superimpose it on top of the other one, and the first one completely blots out the second one, and can pull off the other one and place it on top of the first one and get the same result, then those two things are considered congruent. Doesn't matter if we have to turn it, if we have to move it, or whatever. If those two things can be placed on top of one another and completely blot the other one out, that's considered congruent. And for angles, that happens when two angles are of the same measure. In this case, you can see angles BAC and CAD, those angles are both 40 degrees, so those two angles are in fact congruent. And we have a symbol here for congruency. This applies not only to angles, but to line segments, triangles, things like that. But the symbol for congruent here is an equal sign with a little tilde sitting above it. Let's reach back a couple of slides here. I want to touch base on complementary angles and supplementary angles once again. So here's an angle that is 57 degrees, and I'd like you to find the measure of an angle that is the complement of that angle and the measure of an angle that would be the supplement of that angle. Take some time for that. Welcome back. Well, as you can see, the only difference between finding the complement and the supplement is what do you subtract 57 from? For the first case, you're trying to find an angle that fitted with an angle of 57 degrees would together form a 90-degree angle, and that angle would have to be 33 degrees in order to do that. For the supplement, you do the same thing, except you're finding an angle that fitted together with a 57-degree angle would form a straight angle of 180 degrees. And that angle would have to be 123, so that 123 plus 57 would be 180 degrees. Let's talk about what happens, some more terminology that happens when two lines intersect with each other. Angles 1 and 3 are called vertical angles. They are the angles that are on opposite sides of two lines that are intersecting with each other. And as it turns out, vertical angles are always congruent. So in this case, angle 1 and angle 3, those two angles are congruent angles. In the same way, angles 2 and 4 are also congruent angles. Here's one other piece of terminology to keep in mind. If you have two angles that sort of share a ray, in other words, they're sitting right next to each other, sharing one of the rays that forms the forms their angle, those two angles are considered adjacent angles. So, for example, between angles 1 and 2, there's this ray that's coming out in between them. So they share that ray, don't they? And that makes them adjacent angles. And what's true about adjacent angles when you have two intersecting lines is that those angles are supplementary. Now let's talk about a line that goes through two other lines. We call that first line that's intersecting the other two lines a transversal. It's going through both of those things. So in this case we have a line that's labeled with the lowercase a. Line A is called a transversal since it intersects the other two lines that are labeled B and C here. And it creates an array of 8 different angles here to try and discern here. Well, we actually have terms for some of these angles here. Angles, you can see that there are some angles that are sort of in the interior of the two lines that the transversal goes through. So there are 4 angles that are in the interior of lines B and C. They're sort of in the in-between area there. We call those angles interior angles. It's angles 3, 4, 5, and 6. Those angles are in the interior portion, in between lines B and C. In addition to that, we have 4 other angles that are outside, not in between lines B and C. They're in the outer realms, so to speak. We call those exterior angles. Those are angles 1, 2, 7, and 8. Why do we introduce this terminology? You'll see in a second here. There's one other piece of terminology here, and that is that you can see that angles, let's take a look at angles 1 and 5. 1 and 5 are on the same side of the transversal. They're also above either line B or line C. So they're sort of in the upper right, so to speak. We call those two angles corresponding angles. Another pair of corresponding angles are 2 and 6. They're sort of in the upper left-hand portion of each intersection, aren't they? We have 2 other corresponding angles, angle 3 and angle 7, and lastly angles 4 and 8. And again, you're going to see in a moment why we define all of these terminologies for angles for these kinds of intersecting lines. You're going to here's a little bit more here. Here's a little bit more. Angles 2 and 8, since they are on opposite sides of the transversal, we call them alternate angles. Angles 1 and 7, those are also alternate angles. Angles 3 and 5, now we're looking at the interior angles. Angles 3 and 5 are on opposite sides of that transversal, so we call them alternate angles. And angles 4 and 6 similarly are on opposite sides of that transversal, so once again we call those alternate angles. And in this way we can combine this vocabulary term with some other vocabulary terms from previous slides. Angles 2 and 8. Find those angles there. Those angles are alternate angles. They're also exterior angles, aren't they? We call them alternate exterior angles. Angles 1 and 7, they're also on alternate sides of the transversal and they're exterior, so they're called, you guessed it, alternate exterior angles. Angles 4 and 6, they are alternate angles. They're in the interior part of B and C, lines B and C, so they are called, you guessed it, alternate interior angles. Same thing with angles 3 and 5, another pair of alternate interior angles. So we finally come to the reason why we introduce all these names for these angles. When lines B and C are parallel to each other, then there's a lot of cool things that we can say about these different kinds of angles here. Corresponding angles are suddenly equal. If you have 2 parallel lines that are together cut by a transversal, then corresponding angles should be congruent. Angles 1 and 5 are congruent. Their measures are equal. Angles 2 and 6 are congruent. Angles 3 and 7, 4 and 8, each of those pairs are congruent angles. Their measures are the same. Adjacent angles. like angles 1 and 2. Again, those angles are supplementary. That's actually true regardless of whether or not B and C are parallel, but let's include that nonetheless. Angles 2 and 3, also supplementary. 3 and 4, 1 and 4, 5 and 6, 5 and 8, 7 and 8, 6 and 7. All of those pairs of adjacent angles are supplementary. And lastly, alternate angles are equal, are also congruent with each other. So angles 2 and 8, those are alternate exterior angles. Those two are equal, or they're congruent. Angles 1 and 7, those are alternate exterior angles. Those angles are also congruent. Angles 3 and 5, alternate interior angles. Those angles are congruent. And lastly, angles 4 and 6, those are alternate interior angles. Those angles are congruent. In addition to this, if you have two interior angles that are on the same side of the transversal, an example of that would be angles 3 and 6. Again, these are interior angles that are on the same side of the transversal, or on the left-hand side. And what we say there is that those two angles are supplementary, interestingly enough. So in addition to 3 and 6 being supplementary, angles 4 and 5 are also supplementary. Those angles also add up to 180 degrees. And lastly, exterior angles on the same side of the transversal are also supplementary. These are angles like angle 2 and angle 7. Again, these are angles that are on the same side of the transversal. Those angles are also supplementary to each other. Alternate exterior angles, exterior angles on the same side of the transversal are also supplementary. So angles 2 and 7, supplementary. Angles 1 and 8, also supplementary. So I'm giving you here a problem. Angle 2 has a measure of 125 degrees. You're given the task of finding the measures of all of the other angles there. You have 7 angles to determine what their measures are. Take some time for that. Welcome back. In our efforts to try and find the measures of all the other angles, we found that they actually fall into two groups. 4 angles have a measure of 55 degrees. The other angles have a measure of 125 degrees. We were given that angle 2 is 125 degrees. 2 and 4 are vertical angles. Therefore, 4 is the same size as 2. That's also 125 degrees. 2 and 6 are corresponding angles, therefore those two angles are also congruent, and angle 6 then is also 125 degrees, and angles 2 and 8 are similarly alternate exterior angles, and so they are also congruent. Angles 1 and 2 are adjacent to one another, so they are supplementary, which means that angle 1 is going to be 180 degrees minus 125, or 55 degrees. In the same way, angle 3 angles 3 and 1 are vertical angles, so they are congruent. Therefore, angle 3 is also 55 degrees. Angles 1 and 7 are alternate exterior angles, therefore they are also congruent with each other, and angles 1 and 5 are corresponding angles, so they are also congruent with each other. So we have our last two angles also being 55 degrees, angles 5 and 7. So two groups, four angles being 55 degrees, the other being 125 degrees. Now, an important application of angles and angle measurements is the determination of locations upon the Earth using coordinates of latitude and longitude. Let me show you what I mean here. I've got a picture of the globe here showing angles describing where a given location on the Earth is. There is a location on the equator, as you can see, where we have two coordinates, 0 and 0. I'm moving my cursor into that location right now and circling that. This is a place, every place along this equator is 0 degrees north latitude. It's neither in the northern hemisphere nor is it in the southern hemisphere. It's 0 degrees latitude. Longitude is defined by these, I was almost going to say vertical lines, but they're not really vertical, are they? Because they extend from the North Pole all the way down to the South Pole. And in this case, this one goes down through Greenwich, England, where the latitude-longitude coordinate system was originally invented. So this meridian here, this line that goes from the North Pole to the South Pole, which we call a meridian, is actually considered the boundary point between east and west. And so when we describe a longitude coordinate as being in the eastern hemisphere, we're saying east of this line. And when we describe a location as being in the western hemisphere, we're describing locations that are west of this line. And so we define a location on the Earth based upon what its degree, what this angle is here, describing how north it is of the equator, as well as this angle here, describing how far east it is of this particular line, or west of this particular line. So in this case, what we are seeing here is a location that is 40 degrees north. That's about where our latitude is, by the way. And this location is also 50 degrees east, indicating that this angle right here, which I'm hopefully doing a good job here of outlining for you here, this angle is 40 degrees here, showing that this is 40 degrees north of the equator. This angle here is 40 degrees, and this angle here would be 50 degrees. Right here, this is the center of the Earth, and this angle here would be 50 degrees in the easterly direction, showing this to be 40 degrees north and 50 degrees east. You might be curious to know what our latitude and longitude coordinates are. And I've pulled that up on a separate tab here, and I am showing you actually a map of the northern portion of the Larimer campus of Front Range Community College. And what I'm going to do here is I'm circling Challenger Point, the Challenger Point building, and I'm going to right-click on this, and I can choose the option of what's here. And you can see here at the bottom, it shows the location of Challenger Point. That's one of the instructional buildings here at this campus. And what you can see here is a latitude and longitude coordinate. And here's what they are. We are 40.523233 degrees north of the equator, and we are 105 degrees west. In this case, they're showing it as a negative angle. That's another way of saying that it is west of that prime meridian there that goes through Greenwich, England. So we're in the western hemisphere, and our angle is 105.093494. That's the way we describe those two angles here. Now you'll notice something very interesting here, and that is that these angles are described in two different ways. The first shows our degrees north as 40.523233. That's 40.523233 degrees north. So we've divided degrees up, showing a trailing decimal, taking us out to tenths, hundreds, thousandths, 10,000ths, 100,000ths, millionths of a degree, right there with that last decimal point. So we're describing the latitude at that angle in terms of something down to the millionths of a degree. Pretty accurate. And we can see the same thing here for longitude as well. We've got 6 decimal places here indicating a similar precision out to a millionth of a degree. That's one way of showing this. Let's show another way in which this information is recorded. You'll notice that this again shows 40 degrees just like before, but it's got this other stuff showing 31 and an apostrophe and then 23.6 and a double apostrophe there, or quotation marks you might say, showing once again that this is north latitude and this is west longitude, but after the 105 we see 05 followed by an apostrophe and 36.6 and a double apostrophe. What's that all about? Well, this is another way in which we popularly divide degrees, I should say. And the way in which this is done is that degrees can be divided into what are called minutes. There are 60 minutes within each degree. And so showing here 31 minutes, 31 out of 60, that's a little bit more than half, which is consistent with the fact that we see 40.5 something. That's a little bit more than half of a degree, more than 40 degrees. So it looks a little weird to be able to say 31 minutes is more than half, but if you think of it in terms of 60 minutes in an hour, 31 minutes, it's a little bit more than half of an hour, and in the same way here, 31 minutes is a little bit more than half of a degree. All right, so this particular apostrophe indicates minutes, both here and here. All right, so what are the double apostrophes? Well, as you might be able to guess from the time analogy I just gave you, the double apostrophes indicate not minutes, but seconds. There are 60 seconds within each minute. And combining those things together here, the fact that we have 60 seconds within each minute and 60 minutes within each degree, that means that we have a total of 3,600 seconds within each degree. This is a tiny, tiny, tiny fraction of a degree that each one of these seconds are. And you can see it here, 23.6 seconds for our latitude indication. You can see 36.6 seconds west. So the way that we would say this is 40 degrees, 31 minutes, 23.6 seconds north, and 105 degrees, 5 minutes, 36.6 seconds west. It's another way in which we might describe actually the same location. These two measurements are equivalent, they're just on two separate scales. Here we're showing what are known as decimal degrees, and here what we're showing is degrees, minutes, and seconds. It's just two different scales describing the same quantity. Well, let's talk about how we work with these two systems that help us to divide angle measurements here. But first, before we get to that, let's talk about how we measure angles. We measure angles using a protractor, and I'm showing you here an angle ABC that we wish to measure. And the way that we do that is near the center of the protractor, we place the vertex of the angle. In this case, the vertex of the angle is B, and so that should go right there. And one of the legs of the angle should be along this line here that extends either here out to this end of the protractor or over here to this end of the protractor. It should be one of the two ends, either or. And then lastly, we take a look at the second leg here in terms of where it appears on the scales that you see along here. And you can see there's actually two separate scales. Why are there two separate scales? Well, as it turns out, it's because one is for acute angles and another is for obtuse angles. And so which scale should we use? Well, the answer that comes in asking the question, is this angle obtuse or is it acute? Is it greater than 90 degrees or is it less than 90 degrees? Well, in this case, angle ABC is less than 90 degrees. It is an acute angle, so we use the smaller scale, which is down here. And we can see that the line here lines up basically right in between 30 and 40, indicating that we would estimate this angle as being about 35 degrees. Let's apply this same technique here to measuring angle CBD. Well, in this case, we've lined up ray BD along this end of the protractor here. That's fine. You can see it actually lines up with 0 degrees over here. And then we're again looking at this same ray here, this same leg of the angle going up through C. But in this case, we're not looking at the smaller numbers because this is an obtuse angle. We're looking at the bigger numbers, the larger scale here. And as you can see, once again, looks like we are right in between 140 and 150. So we might measure this angle, or at least estimate it as being 145 degrees. There are far more accurate means of measuring angles in which we can get down to decimal degrees, tenths of a degree, hundredths, thousandths of a degree. There's also plenty of far more accurate tools that we can use to measure these angles in terms of degrees, down to the minute, down to the seconds. But let's see, how do we convert from one to the other here? What I'm showing you here is the two ways in which we can, for example, divide these degrees up here. I'm showing you 63.6125 degrees. That's a decimal degree representation, so this is 63.6125 degrees. Okay, well, how do we represent that in terms of degrees, minutes, and seconds? As it turns out, an equivalent measurement in degrees, minutes, and seconds would be 63 degrees, 36 minutes, 45 seconds. Now, converting back and forth, I'll show you how to do that in just a moment here. Here's how we take, for example, degrees, minutes, seconds, and convert that to decimal degrees. Let's remember that when we're given in the upper left-hand corner here, 63 degrees, 36 minutes, 45 seconds. We can first of all just extract the number 33. We know it's going to be 63. We can extract the number 63 there. We know it's going to be 63 degrees and some change afterwards. All right, so let's start with 63. And then we have 36 minutes. Okay, what are we going to do with the 36 minutes? Well, each minute is 1/60th of a degree. So 36 minutes will be 36/60ths of a degree. Let's find out what that is by dividing those two numbers on your calculator to get 0.6. Okay, and let's add that to the 63 that we've got here. You can see we're lining this up. We're lining that up under the 63 here because we're going to be adding these together. Lastly, we have 45 seconds to add on to this as well, and there are 3,600 seconds in a degree. So that adds another 45 3,600ths of a degree to our total here, which if we divide on the calculator is 0.0125. All right, so we have 3 decimals to add together: 63, 0.6, and 0.0125. And when we add those together, we get our desired result, 63.6125 degrees. So you can see that the way in which we convert from degrees, minutes, seconds to decimal degrees is just through this divide and conquer approach, where we extract the degrees and just make that the whole number. We extract the minutes and divide it by 60. We extract the seconds and divide it by 3,600. And then we add all 3 of those decimals together to get our final result. Well, how do you convert back? Here is our resulting quantity here, 63.6125 degrees. How do we convert that into degrees, minutes, seconds? Well, it's actually pretty similar to what we did before. First we work on the degrees, then we work on the minutes, then we work on the seconds. You could probably guess here that we're just going to take off the 63 from the front here. It's 63.6125 degrees. All right, so it's 63 whole degrees. So let's pull off the 63 whole degrees there, and we'll have that ready and available. What remains is 0.6125 degrees, and let's see how many minutes, how many whole minutes we can pull off of that by taking 0.6125 and multiplying it by 60 minutes. What we get is 36.75 minutes, and what that means is that we have 36 whole minutes that we can extract from that. 36 whole minutes, which will be the next part of our degrees, minutes, seconds. And it's not 36 minutes, it's 36.75 minutes. So what we want to do is extract that 0.75 and say, okay, how many seconds does that represent? Well, this is 0.75 minutes, and so to convert from minutes to seconds, we multiply by just 60 seconds in 1 minute. So 0.75 minutes times 60 seconds per 1 minute. You can see these are actually conversion fractions reminiscent of what we were doing before when we were converting from feet to meters and grams to ounces and so on and so forth. You can see the first one there is 60 minutes per 1 degree. That's a conversion fraction there. We have a second one that we're now working with, which is 60 seconds per 1 minute. All right, so we have 0.75 minutes left over from our previous calculation. So how many seconds is 0.75 minutes? Well, it's 0.75 times 60, or I should say, how many seconds is 0.75 minutes? So we take 0.75 minutes and multiply it by 60 to get 45 seconds. So our resulting compilation here, I should say, is 63 degrees, 36 minutes, and 45 seconds. We're back to where we started. It's again a kind of divide and conquer sort of approach here, in which we pull off the whole number degrees first, then we take the decimal part of what's left over and multiply it by 60 to get the minutes, and then the decimal part of what's left over from that again multiply by 60 so that we can get the seconds. So take some time to do this. Change 115 degrees, 40 minutes, 15 seconds to a decimal degree equivalent. You can round to the nearest thousandth of a degree. So how many decimal places is that? Tenths, hundredths, thousandths. 3 decimal places. You can round to 3 decimal places as you convert that from degrees, minutes, seconds to decimal degrees. Take some time for that. Welcome back. Well, we can see our divide and conquer approach being repeated here once again. 115 degrees, that's our first portion of this that we're going to add together to get our combined total here. We're taking 115 plus 40 minutes, that's 40/60ths of a degree, so that's going to be added to our total. And then lastly, there are 15 seconds here, and each second is 1/3600th of a degree, and so we're adding another 15/3600ths of a degree to this. We get a repeating decimal, 115.67083, and the 3 repeats there, and so when we round to 3 decimal places, that becomes 115.671 degrees. Similarly, let's go in the other direction here. Let's change 25.375 degrees to degrees, minutes, seconds. We're going in the other direction now. Take some time to do that. Welcome back. Well, I hope you'll excuse my fancy flowchart way of showing how this is done. This probably looks very different from the work that you have recorded onto your activity sheet here, but I wanted to show how each calculation flows out of the previous one, hence all of the arrows. Taking 25.375 degrees, I'm first pulling off the whole number part of that. We have 25 degrees, okay, so we figured out the first part of degrees, minutes, seconds. And then we have the remaining 0.375 degrees that we want to see how many minutes we can pull off of that by multiplying by 60. The result is 22.5 minutes. All right, so that's 22 whole minutes that I can pull off of this, and it's 22.5 minutes, so I have to convert that half of a minute into seconds. That's a half of a minute times 60, as you might guess, that's 30 seconds. So the resulting compilation of all of this stuff put together is 25 degrees, 22 minutes, 30 seconds. Well, hopefully that is a good, solid introduction for you, and that makes some sense for you. This is a good time to go through your activity sheet and mark or highlight all of the things that you see as being most important here. There were some foundational concepts that we introduced with this lesson here. What is a point? What's the size of a point? What is a line? What's the size of a line? And what are the characteristics of a line versus a line segment versus a ray? What are the characteristics of a plane? And In addition to that, how do we define what an angle is? How do we label an angle? How do we label a line? How do we label a point? And how do we describe in two different scales the measure of an angle? How do we measure an angle using a protractor? What are the two different scales that we use in measuring angles? And how do we convert from one of those measures to the other? Lastly, there's an awful lot of vocabulary terms that we introduced in terms of types of angles, as well as other vocabulary terms about angles that come into play when you've got lines that are being intersected by a traversing line. Corresponding angles, alternate interior angles, alternate exterior angles, exterior angles on the same side of the transversal, or interior angles on the same side of the transversal, adjacent angles, corresponding angles. What am I missing here? Vertical angles as well. So take some time to compile all of that stuff together so that you've got that information ready available to you for whatever assessment is going to be coming up pretty soon. And of course, you know, there's going to be an exam on this coming up within the next couple of weeks or so. So take some time to do that, and I'll see you in class.